Hello, and welcome to your last lesson of the semester, lesson 4-7. It begins on page 487, and it's called Just a Normal Day. These are the problems that I intend to work on in this lesson. So the quote of this lesson says, "To study the abnormal is the best way of understanding the normal." William James. I'm not sure who he is. We should probably research that. So if you grew up anywhere near maple trees, you're probably familiar with the seed pods they drop by the thousands in the spring. We call them helicopters, at least where I grew up. Like almost all living things, the individual pods vary in size. On any given tree, there's a typical size with some pods bigger and some smaller. On a beautiful spring day, I gathered 100 pods from the maple in my backyard, measured each, then grouped them according to their length. The smallest was 42 millimeters, the largest was 59 millimeters. And in the photo, they're grouped in classes. So similar to what we did in classes, in the groupings of classes in lesson 4-4. So he grouped them in classes of 42 to 43, 44 to 45, 46 to 47, etc. So the width is 2. An interesting thing happened. We see that the largest number of pods have links somewhere in the middle of the range, and the pods in the classes further away from the center have fewer pods. A wide variety of quantities in our world tend to exhibit the same phenomenon. In fact, it's so common that frequency distribution of this type came to be known as normal distributions. That means that if we get really good at studying normal distributions, we'll be able to analyze tons of interesting things in our world. So the first question says, list some things that you think might be normally distributed. Try not to focus strictly on physical sizes. So maybe, I don't know, average number of songs. On a cell phone, that might be one. Average height. And I would say males and females would be different on that one. So average height of males to females. Average number of miles you travel to work. I think I would be considered unusual on that one. Okay, let's dive into the lesson. So page 488, it says, suppose a researcher selects a random sample of 100 adult women, measures their heights, and constructs a histogram. The researcher would probably get a graph similar to the one shown below. Notice that we omitted a scale on the horizontal axis down below. These would be your heights. Put in a scale that you think seems reasonable based on the description of the histogram. What do you think the value right in the middle of the horizontal axis represents? So these would be heights of females. And I would think the mean height would be in the middle. That's what my guess is, the average height, where most people are. And I'm 5'2", maybe 5'3" on a lucky day. So I think the average height might be around 5.5, I'm guessing. So 5'6". And if we did that remember 5 feet 6 inches is the same as 5 times 12 inches. So 60 inches plus 6 inches. So that's 66 inches in height. Just so you remember that, how to turn feet into all inches. Next, the researcher decides to go big or go home, and she chooses big. She dramatically increases the number of women in the sample, and since she has more data to go on, makes the classes narrower as well. Happy with the results, she adds even more women to her sample and makes the classes even more narrower right here. The results would most likely look like the next two graphs. So more women, She's getting more women in the center in these fine groups, so they're smaller. So the size, the width of these groups out here, these classes are probably only going to be maybe here, it would maybe be 6 inches to a foot in each class. And now this might be just like 2 inches, 2 inches, 2 inches all the way from the center. Okay, now let's use some imagination. Suppose that our researcher has magical powers and can continue adding data, improving her histogram until there are infinitely many data points. Wow, that's a lot. Instead of drawing boxes, draw a smooth curve that you think the histogram would become in the long run. So a smooth curve that you think maybe kind of matches this. So I'm going to say that it's going to look something like that, where this is my mean height. Okay, so we're now on page 489. It says, if all went well, you've just drawn your first normal probability distribution or normal curve. We'll see plenty of examples in the remainder of the lesson if you're unsure how well you did. How does the drawing relate to the maple seed pod example from the opening graphs of this lesson? So if we go back, it looks, it's hard to see on my, where I did my pen, but I think it looks pretty good. Fairly close. To show that normal distributions are not even close to a purely mathematical topic, we're going to borrow our definition of normal distribution from an investment site called Investopedia. So a probability distribution that plots all of its values in a symmetrical fashion, symmetrical meaning we could cut it in half and half matches on the left to the right. Symmetrical fashion, and most of the results are situated around the probability's mean, is called the normal distribution. Values are equally likely to plot either above or below the mean. Grouping takes place at values that are close to the mean and then tails off symmetrically away from the mean. So this would be above the mean. And this would be below the mean. And then we would treat this as a number line. So 0 would be somewhere down here. Okay. Next, we'll highlight some of the important features of a normal distribution, which in turn gives us the key features of a data set that is normally distributed. The value in the middle of the distribution, which appears most often in the sample, is the mean. We established that. The distribution is symmetric about the mean. This means that the graph has two halves that are mirror images on either side of the mean. This is the key fact right here. The area under any portion of the curve is the percentage, in decimal form, of course, of data values that fall between the values that begin and end that region. Let's explore the last key point because it's what makes normal distribution so useful in analyzing data. The graph below shows a normal distribution for heights of women in the US. The numbers on the horizontal axis are heights in inches, and some areas are labeled for reference. So we have this here. We have two areas they gave us, and it says, what is the mean height for American women? And that's what's in the center. So that would be 63.7. And these quotes here mean inches. Number 6 says, what percentage of American women are between 57.4 and 59.1? So if we go back to the picture, we're going to look down here where it has 57.4 to 59.1, and we can see the area says 0.03. So area is 0.043. So that tells us, I'm sorry, 0.34. I knew I said that wrong. 0.034. So that tells us that this area, if we turn this into a percentage, tells us that it's approximate. We can't guarantee, right? So approximately 3.4% of adult women are between the heights of 57.4 and 59.1 inches tall. So if you were to say out of 100 women, because a percent is out of 100, out of 100 women, about 3 of them you would expect to be between 57.4 and 59.1 inches tall. So let's look at number 7. It says if there are 31,806 women in the stands for a college football game, how many of them would you expect to be between 63.7 and 66 inches tall? So they gave us that area as well on the previous page. It's 0.303. So that's 30.3% of women will be between 63.7 and 66 inches tall. But they didn't ask us what percent. They asked us how many, right? How many of these women? So how many of 31,806 in the stands will be between 63.7 and 66. Okay, so how many of these, right? So that means we're going to take the percentage. It's how many of these is 30.3% of these. So 30.3% of 31,806 will be, okay, so that's 0.303 times 31,806. Our calculator is 9,637.22 women. And remember, if you can't have part of a woman, which we cannot, then we need to round down. And we're going to round down, not because of the 0.22, but because we can't have, if you have more, if you have 9,638, then you would have just a little bit higher percentage than 30.3. So we're going to say 9,637 women. And that is our answer to lesson check. So the last lesson check of the semester is for question number 7, and it's right there. So now we know that if we have data values that are normally distributed, and if we can find the area under portions of the graph, we can find the percentage of data values that fall in a certain range. That leads to the big question, how in the world do you find areas under the graph? In this lesson, we'll rely on a known rule that allows us to quickly find a range in which most of the data values fall. It's known as the empirical rule. Before seeing the rule, let's make some educated guesses. Okay, so we're going to be developing what's called the empirical rule. So let's highlight this because this is going to be our biggest concept of lesson 4-7. So according to recent research, the mean height for women in the US is 63.7 inches. So there's the center down here, which you already knew, right? And the standard deviation is 2.7 inches. So the normal graph below is marked with the mean and heights that are 1 and 2 standard deviations above and below the mean. So you're wondering probably, how did we get 66.4 and 69.1 and 61 and 58.3? So between here and here, there's 1 standard deviation. So the standard deviation, which has a little letter S, is 2.7 inches. And there's a difference of 2.7 inches. And then there's another difference of 2.7 inches to the second standard deviation. And then there's subtracting 2.7 between these two. And then there's another negative 2.7 subtracting these two. Okay, so meaning this 58.3 is 2 standard deviations, 2 of those S's away from the mean. So I would take 63.7 and subtract 2 times 2.7, which is 5.4. And if I take 63.7 and subtract 5.4, you can see here, I'm going to, oops, I didn't type it correctly. If I take 63.7 and subtract 5.4, I get 58.3 right there. Now to get this last one here, it's 3 standard deviations. So it's -3 standard deviations away. So we would take 63.7 and subtract 3 of those 2.7s. So 63.7 minus 3 times 2.7. And we would be at 55.6. And so likewise, moving to the right, so moving to the left is negative, moving to the right is positive. So this one is 166.4 is this marker right here is 1 standard deviation above, and 69.1 is +2 standard deviations above. And at 63.7, if you're exactly 63.7 inches tall as a woman, you are at 0. You are right at the mean. So you might be wondering, can I fall anywhere in between? What if Mrs. Main, I am 63, about 62.5 inches. So I am underneath the mean. I'm shorter than the average woman, which is not surprising if you've seen me. And not by much though. And I can fall between this. I'm not exactly 1 standard deviation below. I'm maybe like a half a standard deviation below. So we're going to learn how to find exactly how many standard deviations you are below or above the mean as we move on. Okay, so we're going to keep building on this concept. So let's turn to page 491. It says the total shaded area under the entire graph is 1, and this is true for any normal distribution. Explain why. Think carefully about what we know regarding area under a normal curve. So area is the percent of values that are between 2 outcomes of the variable. So from the smallest possible to the largest possible, there should be 100% of values, which equals 1.0 as a decimal. Okay, so all the values possible out there should be under the curve, and that should represent all 100% of data values. So make an educated guess as to what percentage of the total shaded area is between 61 and 66.4 inches. What does this tell us about women's heights? So we need to mark 61 to 66.4. So 61, let's go this way. So 61 is right here to 66.4. Let's see if we know something about the previous page. So we know between 63 and 63.7 and 66 is 30.3. So this is 66.4. So maybe 30 point, let's say 31%. I'm guessing. Okay. And so that's 1 standard deviation. So I'm guessing that there's about another 31% here. So guessing 31 plus 31 is about 62%. It says, based on your answers to question 9, estimate the percentage of area between 63.7 and 66.4. Well, we kind of went backwards, so we already said that. We think that's about 31% because they're symmetric. Now make an educated guess on the percentage of total shaded area between 58.3 and 69.1. 58.3 and 69.1. So now we're saying from here to here. Okay. Do you know anything over here? They said from 59 to 57.4. I don't know. I don't think it's as much as 31% because this was the same width here, but it definitely went up higher. So I'm thinking maybe like 15% in each of these, maybe half of the area. So 15% plus 31 plus 31 plus 15% on the other side. So that would be 92. And this is just a guess. We haven't turned the page yet. So remember, that's just a guess. And you might have a little bit different guess than I do, and that's okay, because we're going to learn more about it here in a moment. The empirical rule here states when data are normally distributed, approximately 68% of the values are within one standard deviation. We were close. We said 62. So they said should be 68%. And then it's because this is one standard deviation away. These were one standard deviation away from the mean. And then it says approximately 95% are within two standard deviations of the mean. So this right here should be 95%. Okay, we were close. And approximately 99.7% of the data are within 3 standard deviations of the mean. Wow, that's a lot of the data, right? So if you're outside of that, we're going to say that you're considered unusual. Okay, so page 492 here gives you the roadmap that you're going to need on your note sheet for the final, because this is kind of the outline that we're going to use. The graph to the right shows an illustration of the empirical rule. Recall that X bar is the mean and S is the standard deviation. So this is the empirical rule. This needs to go on your note sheet. And these percentages are not ever going to change. The only thing that's going to change is the values of your variable. Values of the variable. Okay, so this is what we just talked about on the previous page. The mean of your variable goes here in the middle, and then you're going to add one standard deviation to make this marker, not in between, it goes at this marker, it's a cutoff point. We're going to add 2 standard deviations to get to this cutoff point, and we're going to add 3 to get to the last cutoff point. Okay, so this says that 34% of the data falls between the mean and this cutoff point. An additional 13.5% of the data falls between the first standard deviation cutoff point and the second standard deviation cutoff point. 2.35% of the data falls between the second standard deviation cutoff point and the third. And then out here off by itself is 0.15% of the data. Very, very small. The proportion is 0.0015. So yes, very, very small. So if we want to say that something is unusual, I'm going to have you add this to your graph. Anything outside of here, okay? So anything that is past 2 standard deviations is called unusual. I'm going to highlight this right here, okay? And then I'm going to do the same over here. Anything that is bigger than 2 standard deviations is also called unusual. Okay, so this space right here is unusual. And then this space is unusual. meaning that it's very unlikely to happen if the data truly follows this normal curve. So it says, man, I love M&Ms. And I've met Dave, the author. He does love M&Ms. He uses them in a talk. He likes to use chocolate in his talks. He can't get enough of them. So it says he just ate some peanut butter M&Ms. Not my favorite. No, 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 no. My almonds are my favorite, and then peanuts are my next favorite. When I buy a bag, the last thing I want is to get shorted. So how many M&Ms is enough? According to a fascinating post on joshmadison.com, the mean number of plain M&Ms in a standard vending machine bag is 54.6, with a standard deviation of 1.3. Let's see how we can use the empirical rule to study what's likely to happen when you buy a random bag from a vending machine. So let's go on down to the solved example number 1 here. Assuming that the number of M&Ms in a package is normally distributed, which, by the way, is more likely than likely it is. Is more likely than likely it is. Okay. Draw an empirical rule diagram using the given mean and standard deviation. Okay. They told us that right up here. So the mean, let's just write that out, is 54.6, and the standard deviation is 1.3. So it says if you buy 200, so first let's draw the curve. And it shows how we did that here. You can read through this. So you're going to put your mean down here in the center. We did 517. And if we take 517 on the calculator, right? And we add 1 standard deviation. I just scooped up here. We have to go with what they gave us here. Trying to figure we're using to give them. Okay, if you buy a 200-pound bag, 200 1-pound bags of M&Ms, a number I guarantee I've surpassed in my lifetime. How many would you expect to contain between 505 and 529 M&Ms? Okay, and then we're going to fill in the blanks here and what percentage of bags would fall here. So let's go down how he did this. The most important part of this example is the first part. In order to use the empirical rule, it's always a good idea to draw and label a normal distribution with the values corresponding to the key values from the empirical rule. That means we'll want to start with the mean in the middle, then keep adding and subtracting the standard deviations, since the key values are 1, 2, and 3 standard deviations to the right and to the left. So the mean in this case is 517. And the standard deviation is 12. So this was a different size bag than what he had up here. So I started going with the bag that he had up here. So we're not using this old example did. So his mean in this case is 517 and the standard deviation is 12. So the middle is 517, and then he's going to take 507, clear this out. So 517, and we're going to add 12. So that means this first standard deviation right here is 529. Then I want to pretend that we're going to jump to the next one. I don't want to keep building because I want you to be able to go from the center to the second one. So from the center to the second one, you're going to say 517 plus 2 times that standard deviation, because it's 2 standard deviations above the mean. And that is going to give you 541, just like it says. This is X bar plus 2 S's. The third one is going to be by taking 517 plus 3 of those S's. 3 of those standard deviations to get 553. Okay, now go ahead and see how they calculated the ones to the left. So he took 517 and he subtracted one of the S's to get 505. Let me calculate here. Then he took 517 and he subtracted 2 of the S's, 2 of the standard deviations to get 493. And then 517 subtracting 3 of the S's to get 481. To make sure that that matches. So then part A says, if you buy 200 1-pound bags of M&Ms, how many would you expect to contain between 505 and 529 M&Ms? So 505 is right here. And 529. So we're going to add 34 plus 34. So 68%. If you flip the page, he goes through that, how to get the 68%. Question B says, fill in the blanks. It's likely that 99% of bags contain between blank and blank. So we're not going to start from over here and go left. We want to start from the inside because we want to make sure we're adding the same percent from each side. So we know there's 34 and 34. And so I'm going to subtract 99. So I'm going to say 99 minus my 68, my middle. And then I'm going to divide that 31, divide that by 2 because I need to add equal halves. So that means I'm adding my 13.5 here. So I'm going to subtract 13.5. And then it looks like I'm adding about 2 on either side. So not quite to my third standard deviation. So the way he explains it says, according to the empirical rule, over 99% of all data fall between the mean minus 3 standard deviations and the mean plus. So that's what I said, not quite to 481 and 553, but close. And the third question says, so we would say 481 and 553, but not quite. And the third question says, C, what percentage of bags would you expect to have more than 529? So let's find 529. 529 is right here. This is the cutoff point. It means that you have 13.5% in this group, plus 2.35% in this group, plus 0.15%. So we need to add those before we find out what percentage of the total. And so he does that here. He adds those percentages. So there's a total of 16% in that space. So 16% of bags. So 0.16 times the total number of bags, 229. I'm sorry, 200 bags, sorry, 200 bags times 0.16 is going to be about it asked what percent, didn't it? Yeah, what percent? So it would be about 16%, but that would be about 32 bags. But they really only asked for 16%. Okay, so let's answer a few questions on our own. It says, what percentage of bags have less than 493 bags? What percentage of bags have less than 493 bags? So less than 493 is right here. So that's 0.15% and 2.35%. So let's write that. 0.15% plus 2.35%. So that's 2.5%. And oh, that would be terrible. We have less than 493 when the average is 517. You're really getting shorted. How unusual would it be to get a bag with more than 553 M&Ms or less than 481? So more than 553 M&Ms is this little itty bitty space here. So 0.15% of the time. And then less than 481 is also 0.15% of the time. And both of those would be really terrible, very unusual. Very unusual. And that's because they both fall outside of that 2 standard deviations that we talked about, remember? So anything over in here is unusual. Okay, so let's do our second half of the lesson here. It says, we're on page 494. It says a quantity that can vary randomly from one individual trial to another, like the number of M&Ms in a randomly selected bag, is called a random variable. Why? Because it's random and it can vary. See, math does make sense. If you're really sharp, you may have thought about the connection between the percentages we've been calculating in this lesson and probability. If you haven't, we're going to ask you to do so now. There's a good reason that the normal is called a probability distribution, not a percentage distribution. Using what we know about area under a normal curve and percentage of data values, what does the area under the curve between the 2 data values tell us about probability for a random variable? So we said the percentage has to be between 0% and 100%, right? So that means the probability, and we learned this in lesson 4.1, has to be between 0 and 1, just like the area. So based on the work you did earlier, what's the probability that the next 1-pound bag of M&Ms you buy will have between 529 and 541 M&Ms in it? So 529 is right here and 541. So 13.5%, but it asked in probability. So we would use that as a decimal. So 0.135 probability. Okay. So we're going to add a little piece on now. So it says, as you probably know, there are 2 main standardized college entrance exams, ACT and SAT. Since each has a completely different scoring scale, it's really difficult to compare the scores of students who took different exams. Do you think that scores for these exams are normally distributed? Discuss. And yes, I do. Yes, because the majority of students will score around the mean. And very few will score low. And very few will be very high. Okay. One way to compare statistics drawn from different populations is to compare how far above or below the mean they are. The z-score is a statistical measure that was designed to do exactly that. Okay. So if you have the mean here and you've got your 1 standard deviation to this data value, this data value is 1 standard deviation above the mean. Okay. You should be on page 495. A z-score tells you how many standard deviations a data value is from the mean. The data value on the line above would have a z-score of 1 because it is 1 standard deviation above the mean. Data values that are below the mean would have negative z-scores. Fill in the blanks in the data in the diagram with z-scores using the description at the bottom of the previous page. So if you are actually at the mean, you are not varying from the mean at all. So your z-score is 0. And then if you're 1 standard deviation above, you are at z-score of 1. If you are 2 standard deviations above, you are at z-score of 2. So this would be the 2s. This would be the plus 1s. So then this would be 3. So plus 3s. And so then we're going to go in the negative direction. This would be a -1, a -2, and a -3. So let's look at another solid example. It says a standardized test of intelligence is scaled so that the mean IQ is 100 and the standard deviation is 15. Find the z-scores for a person with an IQ of 85 and one with an IQ of 115. And then what's the probability that a randomly chosen person has an IQ between 85 and 115? Okay, so the person with an 85, so it says this is all about understanding what z-scores actually mean. Notice that the mean is given as 100 and the standard deviation is as 15. That means that 85 is exactly 1 standard deviation below the mean, and 115 is exactly 1 standard deviation above the mean. The z-score for a data value is a number of standard deviations. It is above positive z-score or below, which will be a negative z-score. So 85, 1 standard deviation below the mean corresponds to a z-score of a -1. And 115, 1 standard deviation above the mean corresponds to a z-score of +1. So question B says, what's the probability that a randomly chosen person has an IQ between 85 and 115? Okay, so now we're back to interpreting the empirical rule diagram. We can see that 68% of the area lives between z-score right up here of -1 and 1. That's 34 plus 34. So 68%. So the area is 0.68, and that's the probability that our chosen individual has an IQ between 85 and 115. So let's look at question 5. It says, if the data value has a z-score of blank, then half of the data are below that value and half are above. And that would be only if it falls right at the mean, which is a z-score of 0. We know that the center of a normal distribution is the mean for a random variable. What does question 5 tell you is also true about the center of the distribution? The center of the distribution should be the mean. Question 7 says, a job applicant is told that their IQ score measured in the screening process is higher than 84% of the general population. What was their z-score and their IQ? So 85% was below. Is higher than 84%. So 84% is below their IQ. So let's look at the values here. The mean is 100 and the standard deviation is 15. So I'm going to redraw this. So there was 100, and the 1 standard deviation was at 85 because it's 15 below, and then 15 below 85 is 70, and then 15 below 70 is 55. And again, I'm going by what they told us here. The mean IQ is 100 and the standard deviation is 15. Okay, so 84% is below, so we know at least they're bigger than the mean because this is 50%. Right? Inside here is 34 and then 13.5 and then the smaller values, but this is a total of 50%. So then above the mean, 1 standard deviation is another 34, and that would be 100 plus 15, so 115. So if they were at 115, that would be 84%. Oh, there we go. So 1 standard deviation So their Z is equal to +1, and their IQ must be equal to 115. Because 15 or 50 plus 34 is 84%. Okay. So there is a formula to this, even though we've been kind of working our way through it. The formula says right here, to find the Z-score, if we have sample data, we're going to use the sample symbols. And if we have population data, we're going to use the population symbols. And this symbol here should be that sigma that we learned. They just must have had an error there in the typo. It's your data value. So your data value minus the mean divided by the standard deviation. That's what these symbols mean. X is the data value, the observation, subtracting the mean of the sample divided by the standard deviation. And this is one of those tricky ones where you have to make sure that you're doing the numerator first in parentheses divided by the denominator. So I'm going to use Desmos today when we work through some of these. So there's some notes down here at the bottom that tell us a data point is greater than the mean if the Z is greater than 0 and less than the mean if Z is less than 0. Z-scores have no units, they're unitless. Z-scores are typically rounded to 2 decimal places. So it says 1 year, the ACT had a mean score of 21.2. Let's just write that down. The mean is 21.2, and the standard deviation is 5.1, and that is the ACT. Okay. That same year, the SAT had a mean score of 1060. So the mean was 1060, and the standard deviation of the SAT was 195. And it does vary a little bit from year to year. Suppose that a scholarship committee is considering 2 students, one who scored 26 on the ACT and another who scored 1,230 on the SAT. Both are pretty good scores, but which one is better? That's not so easy to decide because the scales are totally different. So this is what we call, using the Z-score puts them in terms of apples to each other. So they're comparing the same thing. So we're taking ACT and putting it into a Z-score number system. And then we're going to take the SAT and put that into a Z-score number system. And then we can compare them. So first instinct, which score sounds better? I say the person with the high SAT, but I don't know. I'm going to guess the high SAT. Find the Z-score for each test score. So here's the ACT person. Let's find their Z-score. So the ACT student scored 26. So they scored 26, subtracting the average, which is 21.2, divided by the mean of 5.1. I'm going to go to Desmos and show you this work here. So say 26 minus 21, 21.2, parenthesis, and we're going to divide that by the standard deviation of 5.1. So the ACT student was above the mean because it's positive, but only by 0.94, not quite 1 standard deviation. Okay, so let's go back to our paper here, and let's look at the SAT student. So the SAT student, let's calculate their Z-score. So the SAT student scored 1230. Subtracting the mean on the SAT, which is 1060, divided by the standard deviation on the SAT, which is 195. And we're going to go back to, make sure you get that written down. We're going to go back to Desmos and calculate their SAT. And then we're going to use their SAT score to calculate their Z-score. That's what I meant to say. Okay, so here we are. So parenthesis 1230 minus the mean of 1060, parentheses, divided by the standard deviation of 195. So their Z-score, 0.872. Wow. I thought just a higher SAT would mean that they scored better. But if we go back to our paper, we can see that they were both above average because they're both positive. But this one is further away from the mean. It's more positive. It's a larger number. So the ACT student scored better as compared to the SAT student. Very interesting. Okay. So describe exactly what each Z-score tells us. The ACT student scored 0.941 standard deviations above the mean. Oops. Okay. The SAT student scored 0.872 standard deviation. So I'm using SD for standard deviation above the mean. Jeez, if I can't read that. So based on the Z-scores, which would you say was a better score? The ACT, because it is further above the mean. So if we go back to where we drew the Z-scores, here is the mean, the center at Z is 0, and the closer you get to a 1 standard deviation or the Z of 1, you're further from the mean. Okay. So let's look at 12. It says, big sports fans tend to love arguing, and one of their favorite types of argument is who is better, Michael or LeBron, Michael Jordan or LeBron, Joe Montana or Peyton Manning, Kershaw or Koufax. Blogs and airwaves are filled with arguments of this type, and what makes it so difficult to decide is that players and teams from different eras are hard to compare statistically because sports evolve, and that might have been an amazing statistic 50 years ago, completely pedestrian today. Fortunately, this is exactly the kind of thing that studying statistics analytically is good for. The 1942 St. Louis Cardinals were one of the all-time great baseball teams. They won 106 games in an era when teams played only 154 games in a regular season. During the 1942 season, the mean number of games won by a National League team was 75.8 with a standard deviation of 20.5. Another great Cardinals team, St. Louis Cardinals, was the 2004 squad, which won 105 out of 162 games. So they won one less game, but they played many more. In 2004, the mean number of games won by a National League team was 80.9 with a standard deviation of 13.6, which based strictly on winning percentage, the percent of games won, that is, which was the better team. So let's label them by the year, 1942 year and 2004 year. I think that'll be better. Okay, so the 1942 year, they won 106 out of 154 games played. And so that percentage is 0.688 or 68.8% wins. And the 2004 team, they won 105 out of 162 wins. This is going to be smaller because they only won one fewer game, but they played many more. So 64.8% wins. Okay, so it looks like this looks like 1942 looks like they're the better team. So we'll see. So number 13 on page 498 says, use information besides the winning percentages in the preceding paragraphs to make a good statistical argument about which team was better. Obviously, showing your work is a must. Write your final answer in a form of few sentences showing you know what you were talking about. Okay, so I'm going to find the Z-score for the 1942 team and the Z-score for the 2004 team. So the 1942 team had 106 because they talked about just wins, right? The average number of wins and standard deviation. So I'm going to say they won 106 games. And the average one in 1942 was 75.8. And the standard deviation was 20.5. So let's go to StatCrunch and calculate that. So they had 106 minus 75.8 divided by the standard deviation. So the 1942 team was 1.47 standard deviations above the mean. Okay, now let's go ahead and find the Z-score for the 2004 team. They won 105 games. Many more games played. So let's see what the average was for 2004. So they won 105, and the average winning games that season was 80.9. And the standard deviation was only 13.6. So pretty tight. Bigger standard deviation, a bigger difference it looks like in 1942 on the standard deviation, like the variation between the teams was much bigger. So let's look here at the Z-score. Let's go and calculate our Z-score for the 2004 team in decimals here. So we have 105 this time, subtracting 80.9. Divided by 13.6. Okay, so they were actually 1.77 standard deviations above the mean. Let's go back to the paper and just sign this. So I would say 2004 is better, and they play many more games too. So they're comparing apples to apples here. So I would say the 2014. And then number 14 says, look back at your answer to question number 1 on the first page of this lesson. How did you do? Would you be able to come up with more examples now? Of course we would. So that is your last lesson for the semester as far as filling in the workbook. Congratulations, you made it this far. Touch me back for some review for the final exam. Have a great day.